1 over S plus.
Exactly. The inverse of a scalar matrix is 1 over it. In this case,
Yeah.
so that's 0.0018 over S plus 0.111 e to the minus 5S. And GD1 of S is identical, except B, which is 0.018, is replaced by gamma 1 0.0111. So GD1 of S is identical to GU of S, but replacing B, which is 0.0018, by gamma 1, which is 0.0111. So in other words, GD1 of S is 0.0111 over S plus 0.111 e to the minus 5. Any questions? Mika, doing okay? Lila? Selena? Got it? All right. So, let's do an example problem. So these are the transfer functions that we have in this very simple example. So let's ask the question, which is where I stopped last time. So that's a long review, but I think it was needed to bring all the mathematics in context. So here is the first question that I'm going to ask. Assume that the reactor is not under automatic process control. And I'll explain immediately what this assumption means. But all right. APC stands for automatic process control, okay? I want to conserve more space. So I'm just. What does that mean? Well, think logically. The manipulated input is on automatic or on manual. So that means it's on manual. And if I'm not looking at this and adjusting it myself, if it's on manual, what value would it normally have?
Nominal steady state?
Nominal steady state, exactly. Normal operation value. So not being under APC means that U of t is going to be set simply equal to the nominal value. How will the measurement change? If at time 0, so we reset our time, so that's time 0, the feed concentration drops from its nominal value of 0.2 to 0.195 moles per liter. Yes, ma'am.
Would the graph be like up and then down like that?
In this case, no. And in this case, the answer is yes if the reaction is strongly exothermic.
No, for concentration, not for temperature.
No, no, it won't. We'll find out, right? Okay. So, let's see what we can do. We're going to be using the three-step procedure that I have written up there. So, step one is to find the Laplace transforms of all our inputs. Step two, we'll be able to write y prime bar, and we'll see how far we can go with step three. Once we reach a point at step three in which we can go no further, I will interrupt the example and give you part of the partial fractions expansion business. And then we'll finish this example. And then we'll do a second example in which we won't be able to go as far, and then we'll come back and we'll complete the partial fractions expansion. That's how we're going to move today. Clear? All right. So I want to find y of t. So I have these three steps. Step one, find the Laplace transforms of all the inputs that we have. So let's find u prime bar and dr prime. Question? Anybody else? All right. So let's start with u prime bar. We start with what u is, and then we'll find what u prime is, and from that u prime bar. So u, in this case, since we're not under APC, is going to be u naught. What is the definition of any deviation variable?
U naught minus.
Yeah. Real variable minus nominal value. Real minus nominal value. So that's u minus u naught. And what's that in this case? Right? Because u is u naught. And what's the Laplace transform of 0? 0. Okay. Okay. D of t is given as 0.195 for all positive times. At time 0, it changed to 0.195. So for all positive times, it is 0.195. Andrea? Clear? And d prime is d minus d naught. So 0.195. If you look at your notes, what was d naught? Nominal value of 0.2, right? Just a reminder. So the first step is to find, or d1, right? d1. Change that to the 1. Crystal clear? All right. So, here we can just look at the dictionary. What do we have in the dictionary that we can use? A special case, the color chart disappeared, I know the case in the color chart. Right? I don't see any color chart anymore. No to me, green color chart. So, special case of this entry in the dictionary, minus 0.005 is a constant, right? And remember, the constant factors out, so it's the number times the Laplace transform of 1. How do I get 1 out of this? 1 is a special case of this formula. What k and a will give me 1? K1 makes this t to the zeros, which is 1, over 0 factorial, which is 1. So for k equals 1, this becomes 1. And a0, this becomes 1. So if you use k equals 1 and a0, what do you get? 1 over s. So the dictionary, I put here parentheses, given the Laplace transform of 1 is 1 over s, so the Laplace transform of minus 0.05 is going to be minus 0.005 divided by 8. Question?
Why did you make k equals 1?
Because I wanted to reduce to, the whole thing I want to reduce to 1. If I don't choose 1, it will depend on time. It will not be a constant. Okay? So you need k equals 1. All right. So, we found u prime bar and d1 prime. So we are ready? Yes.
So again, you want this value equal to 0 just because u equal to 0?
I want to get the Laplace transform of 1.
Why do you want to get the Laplace transform?
Because I have the Laplace transform of minus 0.005.
Yeah.
That's a constant.
Mm-hmm.
A constant factors out. Okay, here, let me write it down. Laplace transform of minus 0.005 is equal to minus 0.005 and the Laplace transform of 1. That's why I want the Laplace transform of 1 from the dictionary. Okay? Constant factors out. Okay? Okay, now it's good. So, we found d1 prime bar. Move the ball back down again. Step 2, that's the trivial one. Find y prime bar. So, y prime bar is g of s and u prime bar, which is 0, plus gd1 of s times d1 prime bar, which is minus 0.005 over s. So that's going to be equal to minus 0.005 times gd1 of s, which I have up here. So that's minus and I have here, let me write this, minus 5.55 times 10 to the minus 5. Okay, I have 10 to the minus 3 here, and 10 to the minus 2 here. Okay, I see, please note some. Minus 0.00005 5, 5 over s times s plus 0.111 e to the minus 5s. And given how I struggled to make my 5s look different from s's, you see how wise I was to choose 5s for this example in everything. Obviously, I'm being sarcastic. Clear, everyone? Just multiply through d1 times d1 prime bar of s. Everybody clear? And you will allow me, since I have it like that, so to rewrite that. Interesting enough, another 5 here. That's a mess, okay? Hopefully my S is S. So all 5 on S's. It's my very best handwriting. Kevin, okay? 1.
I lost here. After the second equal sign, I have no idea where you get all that stuff from.
This one?
Yeah, I have no idea how that.
Okay, what is GD1 of S? Right here. Minus point.
Oh, okay.
0.111.
Got it. Okay, never mind.
Just substitute them now.
Yeah, sorry, I didn't see that.
Yeah, that's okay. That's fine. Clear?
And why you multiply this one by this one, GD1 is it the same? Like, is it the same problem? You just continue, or?
Yeah, that's the example. Continue the example, yes. Yeah, we continue the example. Okay? We're trying to address this question. So we're going to follow the 3 steps. We follow the 2 easy steps. The work is the 3rd step. Actually, we can do something right away for step 3. Here's an important word to understand. Look at the dictionary. Is there something in the dictionary I can immediately use to write something about y prime of t? The fact that I chose to put only 2 entries, and I already used the first entry, should be a good hint about what we need to use now. Right. So, now we're going from Laplace domain to time. I will have y prime bar. I found y prime bar. I want to find y prime of t. Question? No question? All right. So we want to go from y prime bar to y prime of t. That's inverting the Laplace transform. And if you look at what y prime bar is, we just found it's something times e to the minus 5s. This form of y prime bar, what is this? This is only has s, some function of s. And I have e to the minus 5s. So this is the form of h bar of s times e to the minus ds, which is exactly what I have in the dictionary. So let's write what the dictionary gives me. I immediately have the answer for t less than what time?
5.
5. For t less than 5, y prime of t will be 0. For t less than 5. And it will be